So, this blank slide is going to be all about glucose. So, as we learn all of our pathways in metabolism, we're going to learn it from a carbohydrate sort of focus standpoint to start, and then we'll learn about how we use other fuels like amino acids from proteins or fatty acids from triglycerides as fuel. But right now, we're going to focus on it all being about glucose. So, hopefully, everybody's good with remembering how to draw a structure of glucose and drawing it as a Haworth projection is going to be important because that will allow us to then differentiate how we've got other. So this again is beta D-glucose. And if we remember why this is beta D-glucose, it's beta D-glucose because both of these functional groups are on the same side of the molecule. Alpha D-glucose would have this hydroxyl group down there. But beta D-glucose is nature's favorite sugar because when we consider this as a chair conformer, this is the only configuration of this 6-carbon sugar that can have all of the bulky substituents in equatorial positions. So beta D-glucose is the only one that can do that. And if we consider other isomers of this C6 sugar that we're going to study, if we isomerize at this position and we put the hydroxyl group up there, that's galactose. That's a C4 epimer of glucose. A C2 epimer of glucose, switching the hydrogen and the hydroxyl group at that carbon, is going to give us mannose. Now, fructose is another isomer that has the same molecular formula as glucose, but as we'll see, this is an aldose sugar, meaning if we do ring opening right here, we put our carbonyl containing functional group as an aldehyde on C1, whereas fructose will have the carbonyl on C2. It is a ketose sugar. So we're going to talk about the interconversion of aldose and ketose sugars in glycolysis, specifically between glucose and fructose early on in stage 1. So we'll get to that in a little bit. This is just all about glucose right here. So there's the structure of beta D-glucose. I want to make sure that you're aware of some other names that refer to this same molecule. So dextrose is another name for that same molecule. When we talk about blood sugar, we're actually talking about this molecule in your blood. So blood sugar. Okay, some numbers that we're going to go through as we kind of do this slide, this master slide about glucose, if you will. I do want you to remember that physiological concentration of glucose is 5 millimolar. You actually have a homework question that has you interconvert that with units that are more common in the medical field, which is thinking about glucose concentration as milligrams per deciliter. And sort of a magic number that I want you to remember is 90. Fasting insulin of less than 90 milligrams per deciliter is what's considered sort of healthy blood sugar. So we're going to highlight this here, 90. That's an important number that I want you to remember. Okay, so one of the things that I hope I've articulated clearly is that it is critical to maintaining this level of blood sugar. Too high and it's a problem, it's inflammatory. Too low and it's a problem, and it can lead to some significant complications. So we're going to talk about how we monitor blood sugar towards the very end here. We'll talk about 2 ways that we can monitor blood sugar, both as a snapshot via a glucose meter or sort of a long-term sort of look using something called hemoglobin A1C. Okay, but right now I want to talk about how your body knows that you've got low blood sugar and then how you remedy it. So 2 hormones that are really important for sort of thinking about glucose homeostasis are glucagon. And glucagon is again going to be important for low blood sugar. And we'll get to insulin in just a little bit. That's going to be our high blood sugar sort of hormonal signal. So if we've got increasing concentrations of glucagon that are secreted by your pancreas, that's an indication that you are falling below this critical 5 millimolar glucose. So again, maintaining that 5 millimolar glucose is critical. So there's different ways that we can remedy this. We're going to refer to them as top-down, meaning we're breaking down polymers of glucose to generate glucose, or bottom-up, we're taking non-carbohydrate molecules and making them into glucose. So let's consider the bottom-up approach first. So bottom-up approach is gluconeogenesis. And the purpose of gluconeogenesis is, again, to take non-carbohydrate precursors and we can synthesize them into glucose. So we've got non-carbohydrate precursors, and we're going to be able to synthesize those into glucose. Now, importantly, these non-carbohydrate precursors ultimately are best if they're converted into pyruvate, because pyruvate is the end point of glycolysis, and so glycolysis is a reversible metabolic pathway, and so that we can synthesize glucose from pyruvate. And so that's why we referred to glucogenic amino acids as any amino acids that can ultimately be made into pyruvate. And in doing so, you essentially can convert protein into glucose. So that's our bottom-up approach. That's going to be very important when you're fasting, when there's no type of kind of input of dietary food into your system here. Now, this is the bottom-up approach. We're going to refer to two sort of top-down approaches. And again, these top-down approaches refer to taking glucose polymers and breaking that glycosidic linkage to generate the glucose that we need. So why do I have two arrows here? Where we're going to consider both endogenous sources, endogenous, or exogenous. And if these words are new to you, you want to think about that EX from exogenous, meaning external. So in this case, we're referring to dietary carbohydrates. So specifically things like starches and so forth. So we're going to be able to take those dietary carbohydrates, foods that we eat, and we're going to be able to break them down into that glucose to remedy low blood sugar. So again, we need to break whatever glycosidic linkages we have to get those foods out of the GI tract and ultimately into the bloodstream. Now, endogenous sources, this is also going to be starches. So again, we're going to talk about starch here as plant starch, generally from dietary carbohydrates. But when we're talking about endogenous sources, we're talking about glycogen. So this is going to be glycogen, right? And we learned of that as animal starch. Now, you might remember that you have two main places that you store glycogen in your body. There's muscle glycogen and there's liver glycogen. So this is a really important point. This is only liver glycogen that we're referring to here. Because remember, the muscles do have glycogen reserves, which can be broken down into glucose, but that's only for their own use. It's not for distribution to the bloodstream. We're going to learn a lot more in this semester about how and why that's the case. But when we're talking about a top-down approach of our own internal stores, that's glycogen that's stored in our liver. Now, it's really important to highlight too that this isn't, a forever lasting sort of reserve. This is probably only about 12 hours of carbohydrate stores that are in your liver. And after that point, if you've not consumed any food, you're going to have to sort of revert to this bottom-up approach in gluconeogenesis to synthesize glucose and maintain that 5 millimolar glucose. There's certain tissues that prefer glucose, and then there's cells that require glucose. Red blood cells, not having mitochondria, rely on glucose for their energy. Okay, so lots to think about in terms of how we manage low blood sugar. Okay, but now we're going to talk about and switch to what happens with our other hormonal signal, which is insulin. So just making sure to highlight here, glucagon is going to come over here, and this is going to be for low blood sugar. And then when we've got insulin, insulin is a hormonal signal that tells us that we have high blood sugar. And remember, high blood sugar is very inflammatory. So it's critical that your body finds ways to rapidly lower that blood sugar. So insulin is that important key that allows for GLUT4 receptors to be circulated to the cell surface of particularly your muscle cells, and then bring in that glucose in response to those elevated levels. You also have GLUT2 receptors that are in your liver. Those are always present. So those are also going to be pulling in glucose. They're going to pull in glucose. They're going to either use it directly as an energy source, store it as glycogen. But fundamentally, once you fill up those glycogen reserves, you need to figure out what else to do with that glucose. So we'll get into those details. But high blood sugar, again, is problematic. There's lots of ways that you need to be able to remedy that. So highlighting that we've got both GLUT2 and GLUT4 receptors. So GLUT2 receptors, these are primarily, we've discussed, in your liver. So these are always on or always present. Okay, and then we've got GLUT4 receptors. They are in lots of other tissues, but we've primarily focused on GLUT4 receptors in the liver, and these are ones that are insulin sensitive. Okay, so these are going to be the ones that respond to the presence of insulin, indicating that you've got high blood sugar. They're going to circulate these receptors to the surfaces of the cells to allow the cells to sort of bring in that blood sugar. So remember, high blood sugar is toxic, okay? So we need to think about how we can remedy that, okay? One of the main ways is we use your muscles and your liver sort of as glucose sinks. They're going to pull that in and store it as glycogen. At the end of the day, though, you also have the ability to pee it out, right? And that's why when you have diabetics that have high blood sugar, they're often going to have that glucose that spills over into their urine. Okay, so those are two very kind of rapid ways that your body tries to lower blood sugar. But at the end of the day, the third thing that happens is you have to make it into something. So glucose is going to go through glycolysis. Glycolysis will be upregulated. Glycolysis is a fed state pathway. It's going to help get rid of that glucose, make it into pyruvate, and ultimately that's going to be synthesized and stored as fat. So one thing to remember is that fat synthesis is kind of your body's way of trying to protect yourself potentially from having excess levels of blood sugar. So just putting that down as a list here, the 3 ways that we can sort of get rid of high levels of blood sugar is you can uptake it in your liver, in your muscle. Again, you can have other cells do that, but these are 2 sort of main glucose sinks, as they're going to store it as glycogen. You can pee it out, right, if you've got excess levels of glucose. And so these first 2 are fairly quickly processes to do to either uptake it by glucose transporters into these cells, or kind of have your kidneys allow for it to kind of exit in your urine. A little bit more of a slower process, but nonetheless more important, and no limit in terms of its reserves, is you can synthesize it into triglycerides. Okay, so the last little piece on this kind of concept map that we're going to discuss here is how you actually measure whether your blood sugar is low or whether your blood sugar is high. Now, your body is going to respond by either having glucagon or insulin, but you, as a way of sort of monitoring how that happens, there's 2 main ways that we can think about easily monitoring our blood sugar. So we're going to talk about monitoring blood sugar. So one of the easiest ways to do that is using a glucose meter. Okay, so glucose meters are really a snapshot of whatever your blood sugar is at that instant. So we're going to talk about this as a snapshot. It's actually really cool biochemistry for what happens here. To give you a brief overview, glucose is oxidized in one of those glucose meter strips. It's actually oxidized, and oxidation is loss of electrons. So the amount of glucose is going to be correlated to the amount of electrons that are generated. And electrons are what generate current in a circuit. And so the number of electrons is going to be correlated to the amount of glucose, and that's calibrated within your instrument to tell you what your blood sugar level is. So that's an important tool that we can use to take a snapshot of blood sugar. But blood sugar should fluctuate throughout the day. Now, it shouldn't fluctuate, hugely, but it very easily can fluctuate depending on whether you're fasted or not, whether you're stressed or not, exercising. All of that can kind of cause the cycling of your blood sugar. So another way that we can monitor blood sugar is using a blood test that monitors hemoglobin A1C. So what this is if we think about the sort of the structure of hemoglobin, remember hemoglobin is a protein that lives in your red blood cells that helps to transport oxygen in your circulatory system. there are N-termini in hemoglobin monomers that can be glycosylated. They can form a glycosidic bond to glucose. And in that way, they can kind of tell you how sugary that soup of your blood is. Now, what's really interesting is because your red blood cells live for about 3 to 4 months on average, this really represents sort of a time average over a 3 to 4 month period of how sweet or sugary your blood was. Okay, so it represents a 3-month average of glucose levels. So when we call a glucose meter a snapshot, we're really calling this a kind of a time-lapsed average. So it's a 3 to 4 month sort of average. And there are very simple tables that kind of correlate. This hemoglobin A1C level indicates that your average blood glucose has been this over the past 3 months. But one of the things that I do want you to know, another number that I want you to think about, is the values that we have here for hemoglobin A1C levels. So just to highlight what a hemoglobin A1C level is it really represents a percentage of your hemoglobin that has glucose attached. And so these percentages range from about 4 on the low end to 10 or greater. Okay, so we're thinking again of healthy levels here. So fasting glucose of less than 90 milligrams per deciliter is important. Hemoglobin A1C in the 4 to 5 range is going to be represented as healthy. Kind of standards are if you get above about 5.5 to 6, you're in sort of a pre-diabetic, diabetic sort of category. So hemoglobin A1C, sort of an important measure to think about what your blood sugar on average has been. So a couple of things to think about. If you have anything that sort of affects the turnover of your red blood cells, if red blood cells turn over more quickly, right, you're likely to have a lower hemoglobin A1C. Or if you have some reason that you have red blood cells that hang around a little bit longer, they're going to have more time to get decorated with the glucose, and you're likely to have an elevated hemoglobin A1C. So there's certain things that can change your hemoglobin A1C level. So lot there on sort of a concept map to think about one of your body's main fuel molecules, glucose.